Section 7 is the flip side of Section 6. In Section 6 we were taking the derivative of inverse trig functions, and in this section we are integrating functions that give us results that are inverse trig functions. Yeah, you probably saw it coming. We are not integrating inverse trig functions in this section. We are integrating algebraic functions that wind up giving us inverse trig functions as answers. So keep that in mind. So because of the nature of the derivative of inverse trig functions, they are paired with the only difference being a negative sign. Remember that. The u prime on top in the derivatives was either u prime or negative u prime. We have only 3 integrals involving inverse trig functions to consider. All the co's are very similar to the regular functions, secant, tangent, and sine. The co's are the same. Let u be a differentiable function of x, as usual, and a is greater than 0. Then the integral of du over the square root of a squared minus u squared is the arcsine of u over a plus c. The integral of du over a squared plus u squared, no square root this time, and plus instead of minus, is 1 over a times the arctangent of u over a plus c. And the third one, the integral of du over u times the square root of u squared minus a squared, this time the u and the a are reversed under the square root, equals 1 over a arcsecant, absolute value u over a plus c. So just like before with the derivatives, you need to figure out a way to remember the patterns that are involved in these 3 integrals. These are the only 3 integrals that we need. We don't need this du on top. It can be written over here with a 1 over here, right, in all of those. So just keep that in mind. The du could be, where is it? There it is, over there with a 1 in the numerator each time. It could not be. Typically we'll see it here. Sometimes we won't, though. Sometimes we won't have these exact patterns, or we're going to have to manipulate the integral before we can actually integrate it. That's going to happen quite a bit. So we'll get to that part here in a couple of minutes. We just want to practice a little bit first. It's pattern recognition, really. And once you recognize the pattern, then you can apply those rules of integration. And this is where that one problem not too long ago in the back of the book had an answer that was a trig, inverse trig function, when it came from something algebraic. And we were like, whoa, where'd that come from? Well, this is where it came from. So I have the integral of dx over the square root of 4 minus x squared. So the first thing I want to notice is that I have the dx in the numerator, and I have the square root of 2 things being subtracted in the denominator. That's my first clue that I could integrate this and wind up with an inverse trig function. Okay? Now, the u is going to be this guy, and the a is going to be this guy. A is the constant. So I'm going to call a, not 4, 2. Because then what I have here is 2 squared. The pattern says a squared minus u squared. And I'm going to call u, what? X. So if u is x and a is 2, then what I have here is 2 squared minus u squared. And if I go back to my patterns, which one are we looking at? Arcsine. So come back over here. I can rewrite this if I want to, just to be a little bit more clear. I have the d. Well, technically it's supposed to be du, so I guess I better take the derivative here. And when I do, I get du equals dx. Right? Okay, so I just have du over the square root of 4 turns into 2 squared minus x turns into u squared. So if I go back one more time, that is the exact pattern that we're looking for here. So we can go ahead and integrate it, and this gives us what? x over 2 plus c, we integrated. There's our answer. I'll make that look like an A, not an O. Fork sign. Okay, the second one. First of all, notice the pattern. We have the dx in the top, and we have something plus something in the bottom. If I go back to my 3 patterns here, which one does this most closely resemble? Yeah, the arctangent one. The problem is that's not a perfect square here. Or is it? Yeah, if I take the square root of 2 and then I square it, I wind up with 2. And now this is a perfect square. So I'm tricking the math a little bit here. Okay, so let's do the same thing that we did before. We have A equals what? 2. Not 2. It's the square root of 2. U is going to be what?
3x.
Why 3x?
Because 9x squared is the perfect square. So because 3x times 3x is just 9x squared.
That's right. We don't want 9x squared. We want this to be u squared sitting here. So therefore, we have to use 3x, because then 3x squared is 9x squared, as we see. So then I also need to take du equals what? 3 dx. Okay, so there's a problem here. What's the problem? Can't we just? We need to solve for dx, because all I have here is a dx, right? Or I can think of it like this. I have a 3 dx. If I had a 3 sitting here, then I'd have 3 dx in the numerator. It should be fine. But to keep this thing in balance, I got to put a 1/3 out front. Okay? Just little tricks of math get this thing into the pattern that we need. Is that everything we need to do? Yeah? Now, do we need to rewrite it? Let's go back and take a look at arctangent one more time. We have the du here. We have the a squared, and we have the u squared. So let's go ahead and rewrite it so we have exactly what it is that we're looking at here. We have the 1/3 out front, integral, 3 dx turns into du over, now we have the square root of 2 squared, still, plus what? Well, u squared is, so u is 3x squared. Now we pull straight off of this the pattern for the integral for arctangent, or that gives us arctangent, and the pattern is what? 1 over a. Don't forget the 1/3 times 1 over the square root of 2 times arctangent u over a, 3x over the square root of 2. Don't forget your plus c. We can combine this, so that gives us 1 over 3 root 2 arc tangent 3x over root 2 plus c. If you need to, with the roots in the bottom, we've been dealing with roots in the bottom all year long, and we've been kind of letting that go. If you need to, on a multiple choice test, you can rationalize this and it would become the square root of 2 over 6. You can rationalize this and it would become 3 root 2x over 2. But you don't have to. Unless on a multiple choice test, it looks like they did. Okay? Seems like we're probably using secant on the last one since we haven't yet. But actually, if you look at the pattern here, and we look back at the pattern for secant, we do have that something outside the square root of the u out front minus the a. So, oops, wrong way, this way. We have the u minus the a, and we do have that something out front. Notice, though, that that something is supposed to be u, right? Okay. So what do we need to do here? A is 3 for sure. U equals 2x. Good. Because this has to be u squared sitting here. So 2x. And then du equals 2 dx. Solve for du. Solve for dx. Yeah, remember that this is supposed to be u out front here. U was 2x, so I actually need a 2 here. Agreed? Okay, now if I put a 2 here to keep this thing in balance, I have to put a 2 outside, or I have to put a 2 up here. And now notice that I have 2 dx, and I have 2 dx sitting right here. So this all right here, this can be written like that, and now I have du in the numerator. So I actually didn't have to create, it just automatically did it for me once I made that pattern. Okay, so let's see if we can rewrite this. We have what? Well, 2 dx turns into what? Du over u square root u squared minus 3 squared, which is the pattern. Okay, so now we can go ahead and integrate that thing. We're using secant, and the result is 1/3? 1 over a, that's right. So 1 over 3. Okay. Absolute value of 2x over a, which is 3, plus c. Okay, so these three integrals are basically using, or recognizing and then using patterns, or manipulating until you get the pattern that you're looking for, and then going ahead and integrating. Otherwise, you're not going to be either not going to be able to integrate, or it's going to be a real struggle trying to integrate these. So you want to definitely try to use the inverse trig integral rules that we just learned. Okay, so as usual, the first examples that we see are kind of the more obvious ones, or the no-brainer ones, or the ones that don't take a whole lot of effort or work to manipulate. So you may need to manipulate the problem to give up the pattern, as I've already said. One way is to use a u substitution to make the pattern work. We've actually already been using u substitutions so far. But now we're going to have to really do a u substitution here. So with this one, first of all, what pattern does this one kind of look like? It would be a u minus a in the denominator, right? So that looks more like secant to me, or the arcsecant one. So I'm going to, because of the fact that we have that square root, it's definitely not tangent, right? Because of the fact that I have the variable in the first term minus the constant in the second term in the denominator, I'm thinking it's probably the arcsecant pattern that I'm trying to find. So somehow this is going to have to give up the arcsecant pattern. What I need to do is pick a reasonable u. It seems like 2x, because that's how we normally deal with e to the u situations. But it's not. Remember that this needs to be u squared sitting here. E to the x, that's right. So let me off to the side, let me write, if I have e to the x and I square it, when you raise a power to a power, you multiply. So if I multiply 2 times x, I get e to the 2x. So e to the x, actually, is a good u. So that makes du, what? E to the x dx. Don't forget the dx. It's kind of a vital thing to this problem. So now we have this dx sitting in the numerator. We want to switch that into something in terms of du. So I'm going to divide both sides by dx. When I do that, I get 1 over, divide both sides by e to the x. 1 over e to the x du equals dx. Hopefully you're with me so far. Okay. Well, what is e to the x? It's just u. So actually what I have here is 1 over u du equals dx. Now I can substitute that in up here. This is actually u squared minus, I could write that as 1 squared because 1 squared is just 1, right? So now let me rewrite what I have. I have the integral of 1 over u du divided by the square root of u squared minus 1 squared. Now all I need to do is realize that this 1 over u right here can actually be written as the integral of du over u times the square root of u squared minus 1 squared. That fraction winds up just putting that denominator into our denominator. And now this is the pattern for arcsecant. So we can go ahead and integrate, and what are we going to get? So what is that first part? It's 1 over a, which is 1. So we have 1 over 1. Okay? Absolute value of u is e to the x. Plus c. So now we can simplify that answer. Parentheses e to the x, because even if I plug in a negative number for x, it's always still going to be positive. It's going to be very small, but it'll be positive. So I don't need the absolute value. And actually, because it's e to the x, I don't even need parentheses. Plus c. There's your answer. Okay, another method is through rewriting. What? We always forget to rewrite, I know. So we need to rewrite as a sum of two quotients. What is another single word for rewrite as a sum of two quotients? Split. Did everybody hear that?
Split. Jump.
I'm still not sure everybody heard it. Okay, so notice that we have the square root of a squared minus u squared situation going on in the denominator. The numerator has two terms though. So that's going to make it tough to go straight to one of our inverse trig situations. So what I want to do is realize that this is just one thing in the denominator, and if I split this thing, then I'll have one term in the numerator for one part, and then one term in the numerator for the second part, and probably I can handle both of those integrals a little bit easier than I can handle this one on its own. So, split it up. This becomes the integral of x over the square root of 4 minus x squared. And I'm going to use two different colors. Oh yeah, thanks, dx. And then plus the integral of 2 over the square root of 4 minus x squared dx. I'm using two different colors so that we can see as I work what I'm doing for each individual term. All right, let me go back to the blue one here. How can I integrate that? Find a pattern. Does this match one of our patterns? Does it?
Pretty dang close.
We can make it match?
We can rewrite it. We have the technology.
We do have the technology. Just because we now know how to use these inverse trig functions, or inverse trig integrals doesn't mean it's always going to now be an inverse trig integral. We don't have a quotient rule for integrals. On this one, I like maybe using one of our inverse trig integrals, because on this one, it's just a constant in the numerator. But on this one, with that variable in the numerator, chances are inverse trig integral isn't going to work so well. We could go to a u prime over u, maybe, if that's the case, and we could use the log rule. Or we could just do the u substitution and see if we can get this thing to be rewritten in terms of u. Either way, we're going to have to do that.
All right.
So we need to pick a u.
I'm going to say 4 minus x squared.
4 minus x squared. So now this is the square root of u in the denominator. Du equals negative 2x dx. I have x dx sitting right here in the numerator. So solve for x dx. Negative 1/2 du equals x dx. And now this turns into stuff in terms of u. This is u. And now this integral has turned into something that I can handle very easily. Okay, so let's rewrite this now. We have the integral. Negative 1/2 the integral, good. Okay, so this is du over the square root of u, which in your mind you turned into negative 1/2 integral u to the negative 1/2 du. Is that an integral we can take?
Yes.
Yes. So in this case, the inverse trig situation didn't need to happen because I defined a u that worked and simplified this thing down to something that I could easily do. In this case, this looks more like the pattern for one of our inverse trig integrals. Which one does this look like? Arcsine, because we have in the denominator the square root of a minus u, a squared minus u squared. So this does look a little bit more like arcsine. So let me switch colors again. And for this one, what do we need to say here? A is 2. U is x. Okay, take the derivative of u, du equals dx. Is that all we got to do? We do have that 2. What can I do with that 2? Bring the 2 out. If you were to put a 1/2 out front, you'd be changing this whole thing. To put a 1/2 out front, I'd have to put another 2 up here to keep it in balance. Just pull the 2 out. So now we have plus what? Technically it's a 1 up there now, but then the dx turns into du, so I can write the du up top. Or I could write minus u squared. That just kind of solidifies in my head that I actually do have that pattern. So this is the arcsine pattern. All right, so just to finish this one off down here, all right, plus, I'll just do it again. Integral du over square root 2 squared minus u squared. Okay, so now we're ready to integrate. Oh, go back to blue, and what do we get? Okay, so we're integrating u to the negative 1/2, which means we're going to have u to the positive 1/2, and then we got to divide by 1/2, which is just the same as multiplying by 2. So actually what I have here is 2u to the 1/2. Okay, just check your thoughts on that. The 1/2 comes down if I take the derivative. 1/2 times 2 is gone, and I'm left with the negative 1/2, which is, okay, so we did it right. All right, now what? Close it? Okay. What about that 2? 2 arc sine. So x over, okay. All right. These 2's here go away. What about these 2's here? No, because this is something enclosed in that trig function. So no. These 2's here, though, do. So I have negative, what? Plus the stuff. Okay. So this is the square root, right? So I could write square root here. So that's a possibility. Can I take the square root of each of these numbers here? If you're thinking yes, then think about this. What is the square root of 4 plus 9? Is it 2 plus 3, which is 5? No, we can't. So you can't take this square root if you were to write it as a square root. So be careful about that one. But this is a good enough answer right here. We're done. Another way that you might need to manipulate is by completing the square. If you notice, all of those integrals that we've been working with so far have like perfect square situations going on. It's a perfect square plus a perfect square minus perfect square underneath the square root. So if you're dealing with perfect squares, you might need to complete the square, especially if you're dealing with a polynomial in the denominator. So let's remember how to complete the square. Did we remember how to complete the square? We need to remember how to complete the square. So I'm just off to the side, I'll use the same polynomial, x squared minus 4x plus 7. To complete the square, I need to boot this guy over here. X squared minus 4x plus 7. What I'm doing is I'm making a perfect square trinomial right here by adding or subtracting something inside. Then to keep things in balance, I have to undo what I did outside. All right, so to make this a perfect square trinomial, what do we need to do? Yes, but there's a faster way. No, we don't even have to do that. The fast way to complete the square is to take b, divide it by 2, and then square it. So it's positive 4. The important thing is we took this number right here, whatever it was, divided it by 2, and then squared it. That gives me a perfect square trinomial here. Now I just added 4 inside, which means I got to subtract 4 outside to keep this thing in balance. And now once I've done that, this turns into x minus 2 squared plus 3.
And now, now we have
The dark tangent. So this rewrites as dx over x minus 2 squared plus 3. And that does look a heck of a lot like the dark tangent. It's not?
Because we need the 3 squared.
Oh, I guess we can just switch.
Let me call stuff by u and a, all right? So a is going to be what? Has to be the square root of 3 because this needs to be a perfect square sitting here. So I'm turning that into the square root of 3 squared. X minus 2, which makes just dx. Okay, so this turns into du. This is u. This is a. Now do I have? Oh, because tangent is written as a squared plus u squared in the denominator. But we have u squared plus a squared in the denominator. With addition, can we swap? 2 plus 3 is the same as 3 plus 2. So this is the arctangent.
I'll allow it.
You'll allow it? All right. So what do we have then?
We're going to go du over this stuff, so basically 1 over a.
Oh, you don't want to write that down? Okay.
It's just
1 over the square root of 3. Arctangent of u over a, so u is over, yeah. Is that it? That's it. You're done. You don't need to. You're done. Yes, you could rationalize this. Yes, you could rationalize this, but you don't need to. That's it. Sort of the theme for this whole semester has been finding the area under a curve. So once we learn how to integrate something new, then we can do that sort of thing again. And in fact, that's where we're headed from here on out, is finding the area under the curve in fun ways. So find the area of the region bounded by the graph of that, and there I've given it to you, the x-axis, and the lines x equals 3 halves and x equals 9/4. So 3 halves is like 1 1/2, so right here. And 9/4, I have no idea what that is, 2 1/4. So that's right there. So I'm trying to find this little region right here. So what do I do? Integrate. What am I integrating?
from 3 1/2
So 3 halves to 9/4. All right, so that's the setup.
We're going to let u.
Well, before we do that, does this look like something we can use a...
Yeah, it's not a constant like a.
All right, so that's a problem. Yep.
So we're going to let u equal.
We're actually not. What did we just do on the last problem?
No.
We completed the square. Yeah.
It's all coming full square.
Oh, we got.
Complete the square. So first of all, I'll rewrite this thing. So off to the side, I'm going to have 3x minus x squared, right? Now I'm trying to complete the square, which means I need the x squared term first.
We got negative x.
Negative x squared plus 3x. That's a problem. You can't have a negative out front.
Multiply it by negative.
So factor out the negative, and now you have x squared minus 3x, and now I can complete the square.
Divide by 2 squared.
Divide this by 2, and then square it, and you get 9/4. So plus 9/4. We need to keep this in balance, but we have a negative out front, so actually we just subtracted 9/4, which means we need to add 9/4 outside. Not 9/8, 9/4. All right, so now this is a perfect square trinomial. I can write it like one. Negative, parentheses, x minus 3 halves squared plus 9/4. And by doing that, notice that now I have a situation here better than the situation that I had right here. Now I don't have a variable in that front term, which was kind of giving us heartburn to begin with, okay? And we can switch these around, so now I have 9/4 minus x minus 3 halves squared. Oh, and by the way, look at 9/4. What is it? a perfect square. This is actually 3 halves squared minus x minus 3 halves squared.
And that one is,
So now let me rewrite this. We have the integral 3 halves, 9/4, 1 over square root 3 halves squared minus x minus 3 halves squared dx. Which pattern do we have?
Sine.
Looks like sine?
Yeah.
Arc sine? Yeah. Do we have the pattern right now? Yeah?
well, we have to let u equal x squared 3 halves,
But then du would just be dx. So this is taken care of. And then this is...
we could do the substitution and get it down.
Why do you?
I like the thought.
You are so.
I like that thought, but we're not going to do that. We're going to go ahead and integrate this as is. So, what do we get? Arc sine x minus 3 halves, so u over a 3 halves. We're going from 3 halves to 9/4. So this is a nasty looking little composite fraction right here. What if we can't use the calculator?
Well, we got sine, so we're going to try and do sine.
You can leave answers as exact values, and we're going to. Okay, so we're going to evaluate this now. It goes from, we're starting at 9/4. So if I plug 9/4 in here, I have 9/4 minus 3 halves.
0. Yeah.
9/4 minus 3 halves. 3 halves turns into 6/4. So I have 9/4 minus 6/4, which is 3/4. Divided by 3 halves,
6 12s,
which is 1/2.
1/2.
So we have arc sine 1/2 minus. Now we have 3 halves minus 3 halves, which is probably still 0. Divided by 3 halves, right about 0. So arc sine 0. When is sine 0? 0.
So arc sine 1/2.
When is arc sine, or when is sine 1/2? Pi over 6. Minus 0, which is pi over 6. That's your answer. You do that on a calculator, you get a decimal approximation, and you'll never understand that it's pi over 6. You have now learned all of the integrals that we are going to be learning this entire year in this class.
Once again, boys, we've made it.
There are 20 of them. Take a look at those 20 rules. They are all on the inside cover of your book. And it is expected that you know them and are able to use them easily on the AP exam. You need to know them by heart. Most of them you know already, but some of them you just recently learned, so make sure that you do know them and are able to use all of them at the drop of a hat.